I'm Johnny.
Hey, I'm Max, and this is our video presentation for Algebra subject in Aerospace Engineering degree for Universidad Europea de Madrid. This project is about complex numbers. We are going to reach following objectives, such as general problems, solving problems. Stay with us.
So now we are going to see the following example. f(x) is equal to x squared plus 1. If we draw this function, we get a parabola. To see where the equation is equal to 0, we must look where the parabola crosses the x-axis. But our parabola doesn't cross the x-axis, so is there no solution? What can we do to solve this equation? 200 years ago, Gauss proved something that will be useful for us. Polynomial of degree n have exactly n roots. Because our equation has a degree of 2, it should have 2 roots. According to the fundamental theorem of algebra, our plot disagrees with it. But what Gauss is telling us is that there are 2 good values of x that we could use in our function and get 0. Where are these 2 missing roots? The easier answer to this question is that we don't have enough numbers. We normally think of numbers as a one-dimensional continuum line. We can see here 0, 1, 2, negative numbers, fractions, and even squares. But this system is incomplete, and there are missing numbers, which are not even in the left or the right of our line. There are new dimensional numbers. Dimension has everything to do with a problem that was considered impossible to solve for over 2,000 years. Seeing our input numbers in their full dimensional form, we can see how function x really behaves. Finally, it crosses the x-axis. The only problem was that we were looking in the wrong dimension. So, why haven't they given us the numbers at the beginning? This is because they are not real numbers. What is the connection between complex multiplication and complex plane? To see it, we are gonna see 4 examples. For each one, we plot the number that are multiplying together and compute the result algebraically and plot it. Now, we have to search for patterns. We have to keep track on the angular complex number with the real axis by determining our angle using the arc-tangent function. After resolving, we see that the result angles are exactly the same to the angles of the numbers that are multiplying added together. Now we are halfway in our connection between complex multiplication and complex plane. When multiplying on a complex plane, the resultant angle is equal to the sum of angles of the number we are multiplying. Now let's look at these 2 examples. The angles are identical, but the complex number is not. So we just can't keep track on the angles alone to describe complex multiplication in a complex plane. What is the difference between these examples? Let's see. Multiplying by 2i has pushed a result further from origin than multiplying just by I. By how much further? We can measure the distance between the origin and our complex number by forming a right triangle and using Pythagorean's theorem. As before, let's compute our measurements for each example and look for patterns. We can see that if we multiply distances, we obtain the distance from origin. We now have a complete picture. When we multiply complex numbers on the complex plane, the angles form the real axis and their distance from the origin multiply. This is the connection we are looking for. We have a complete equivalent interpretations of complex multiply. To multiply 2 complex numbers together, we can follow the rules of algebra, or we can find each number's distance from the origin and the angle to the real axis on the complex plane, and multiply and add each one. And what is cool here is that this operation looks and are totally different, but they do exactly the same thing. Let's solve a simple equation. X cubed is equal to 1. What value of x makes this equation work? If you set x equal to 1, 1 cubed is 1, so we got the answer. But there are more answers. In the first part of this video, we introduced the fundamental theorem of algebra, which says polynomials of degree n have exactly n roots. If we rearrange our equation as x cubed minus 1 equals to 0 to make it a more obvious polynomial, our degree is 3, so the equation must have 3 solutions. There is an algebraic way to find all 3 answers, but it involves perfect cube factorizing in the quadratic formula, and it may take some work. Instead, let's try solve this problem using a complex plane. Our question is, what number when multiplied by themselves 3 times is equal to 1? Let's think this problem using the polar form of complex numbers. We can think about one of the complex plane as the number with a magnitude of 1 and an angle of 0 or 360. We multiply numbers in the complex domain, the magnitude in the angles are multiplied. As a result, we should have a magnitude of 1, since 1 times 1 times 1 is 1. If we give each other of our axes a magnitude of 1, the resulting magnitude will equal to 1. Easy. But what about angles? We know when multiplying complex numbers and angles, we need an angle that when we add it together 3 times gives 0 or 360. 360 seems more reasonable, so what's the correct answer here? Since we are dividing 360 into 3 even parts, the right answer here is 360 minus 3 or 120 degrees. When we put this together with the magnitude of 1, we have a second solution. This answer makes a lot of sense in the complex plane. Multiplying our answer by itself once, it results in a magnitude of 1 and an angle of 240 degrees. And multiplying it again, we get exactly what we want to get, a magnitude of 1 and an angle of 360, also known as the real number 1. Our teacher would like this answer, so let's put it back in the rectangular form. Our best friend, the unit circle, can save us some time here. We would like to know the rectangular coordinates of a point on the unit circle at an angle of 120 degrees. According to the unit circle, our answer is minus 1/2 of the real part root 3 over 2 for the imaginary part. So now let's try. Multiplying our results, we have 1. Yes, we solved the problem visually using complex plane and get the same answer when factorized. Perfect. But wait a moment, we only have found 2 results and we must find 3. We can find our missing answer going all the way around the circle. If we start at minus 1, 20, and we multiply our number together 3 times, we also get the real number 1. So our missing answer is negative 1/2 minus root 3 over 2i. So now we found all the answers to our problem.